So today we will be talking about the electric charges, which are the source of the electric field, as you know. Now, this will be a review of most of the things that you know actually from high school. So to start with, you know that there are two types of electric charges called positive charge and negative charge, with of course the negative charges being, the negative charges being the type of charges processed by the electrons, and the positive charges are the type processed by the protons. This is something that you all know. Now, how do we charge an object? When I talk about an object here, we will be mainly meaning objects that are macroscopic objects. I mean, like a small sphere, like a rod, or something of this sort. So how do you charge an object? First of all, well, what is an uncharged object? It is a neutral object. And as you know, a neutral object is an object which has the same amount of electrons or protons. That is, it has the same amount of these positive tiny constituents of matter, which are the electrons and the protons. So if it has equal amount of these, an object have equal amount of these, then that object is neutral, it's uncharged. So how do we charge this object? Well, the idea is just to break this balance between the electrons and the protons, or between the negative charge and the positive charge. And how we do this? Well, if it has a deficiency of electrons, that is, if you take electrons from that charged object, then in this case you will have an excess of protons, a positive charge. So we say that object in this case is positively charged. Now, if it is the other way around, if you add, if it has an excess of electrons, that if somehow you add electrons so that the electrons become more than the positive charge, which is the protons in this case, then this object will be negatively charged. Okay, so having a microscopic object charged is about having a deficiency of electrons. In this case, it will be positive charged, which means you have taken electrons from that object, or having an excess of electrons, which in this case, it will be negatively charged in this case, and this means that you have added electrons to that microscopic object. Now, how you can transfer electrons from or to a macroscopic object, some object that you use in daily life? Usually, we will talk about two ways here. The first one is by rubbing, which we will just discuss soon, and the other is called induction. This happens for conductors, and you do not have any contact in order to do this. Now, more about electric charges. Now, this is something you know, that charges of the same sign repel one another, and charges of equal signs attract each other. So this is something that everybody knows. Now, there's an important point here, which is the conservation of electric charge. And this is one of the fundamental conservation laws of nature, actually. You remember probably we talked about conservation laws of nature before when we talked about mechanics. If you recall, we talked about conservation of energy, we talked about conservation of momentum, linear momentum, we talked about conservation of angular momentum. So one of the other fundamental conservation laws of nature is actually the conservation of electric charge. And to understand what does this mean, there are many ways to formulate this law actually, at what level you choose actually to formulate it. But for our purpose in this course, we will be formulating this by saying the following, that if you have an isolated system, then the electric charge in that isolated system is conserved. What does this mean? First, an isolated system in this case means a system where no electrons or protons are allowed to are entering or leaving that system. So in this case, this is the meaning of an isolated system. Now, in such a system, if you add up all the positive charge and the negative charge in that system, the sum will always be constant, and it will not change. If it were 0, then it will always be 0. If it was plus 10, it will always be plus 10. If it was minus 1 million, it will be always minus 1 million, the sum of the positive and negative charges. So why? Because this is a manifestation of the conservation of electric charge. This exhibits itself, for example, if you look at charging an object by rubbing, which will be considered shortly. In this case, charge goes from one object to other, so it doesn't disappear. I will just discuss this when I show it graphically. So this is conservation of electric charge, and it is an important point. Now, charge is measured in units of Coulomb. The SI unit of measuring charge is the Coulomb. Okay, now this is just a graphical representation of things that we talked about. So as you can see here, if you have a glass rod carrying positive charge, and you have a rubber rod, for example, carrying negative charge, and then you make this in contact with it, it will attract it. These will repel each other, for example, because they carry the same charge. Now, what I want to talk about here is actually which is charging by rubbing. Charging by rubbing, here we have a specific example where we have a glass rod and we have like a silk cloth. Now, if you rub the glass rod with this silk, then you will start noting that they will start attracting each other. Okay, this means they carry electric charge in a way. And what's happening in this case is that part of the, so this is one way of charging an object, which is rubbing. By rubbing, you are mechanically, this mechanical force somehow makes the electron move from one object to another. In this case, the glass, which is originally a neutral object, has the same number of electrons and protons. The same apply for the cloth. Originally it was neutral. Now when they are rubbed, what happens is that part of the electrons in the glass move to the silk cloth. In this case, we will have a deficiency of electrons in the glass rod, and so a positive charge will appear on that. And we will have an excess of electrons in the silk cloth, so that a negative charge will appear here. Okay, so this is how you charge an object by rubbing. You need two objects and you rub them together. Charge electrons gets transferred from one to the other. Now, conservation of charge here is manifested by doing the following. Before you rub those objects, there was no net charge on the glass rod, neither there were any net charge on the silk cloth. This means that the number of protons, in this case, total number of protons here in the system of cloth and rod was equal to the total number of electrons. So when you add them up, you get 0. Okay. Now, after you rub them, okay, we have now positive charge appearing on the glass rod and a negative charge appearing on the silk cloth. But if you add up all the positive charge plus all the negative charge constituting this system, now it is the same, because the amount of negative charge that appears on the cloth is exactly equal to the amount of positive charge that appears on the glass. So when you add them up, you get equally 0, which is what you had in hand before rubbing. Okay, this is because, of course, I'm neglecting here, or I'm assuming that no charge has been transferred to the air. So this system, which is composed of the rod and the cloth, is an isolated system. Under these conditions, the amount of positive charge appearing here will be equal to the amount of negative charge appearing on the cloth. So this is this is a manifestation of the conservation of electric charge that I have talked about. Now, check this point before you proceed. Okay, another property of electric charge, which is that it is quantized. Now, we'll try to make this to tell you what does this really mean. First, usually we use Q as a symbol to refer to charge all the time. You know, it is not something that is sacred and cannot change, but it's a convention and almost became universal. That is, when you want to refer to charge, you use Q, and this is what we are going to use actually throughout our throughout the course in this case. Now, the electron and the proton have the smallest charge that a free particle can carry. I mean, we have never observed a free particle that carries a charge which is smaller than the charge carried by a proton or an electron. This charge, we refer to it as E. E is a positive number in this case, and it's equal 1.6 times 10 to the power minus 19 coulombs. Now, the charge of the electron, Q, is minus this E, and the charge of the proton is plus this E. Now, since I have said that a macroscopic object will have a charge if it has excess of electrons or protons, then in this case, we expect that the charge will be, and since the smallest possible charge that have been observed by a particle that is free, I'm saying this just a parenthesis because quarks, which are the constituents of protons, for example, they can have a fraction of this charge, but we have never observed a quark that is free, and we think our knowledge up to date says that quarks cannot exist as free particles. They come in groups of 2 or 3 that forms protons or similar objects. So this is why we say that the smallest observable charge by a free particle is actually this E. So therefore, since matter is, charged objects are just objects which have excess or deficiency of electrons, for example, then in this case we accept that the charge that appears on them will be an integer multiple of the electron. So we come with this important relation that any electric charge that that you can ever observe is actually a positive or negative number n multiplied by E. So if you have an object which is negatively charged in this case, then actually the charge on that will be minus multiplied by n multiplied by E. Or in other words, it will be an integer multiple of the charge of the electron. If it has a positive charge, then it will be an integer multiple of the charge of proton. So it's positive E multiplied by n. Okay. So and where n is an integer. So this is the idea of the conservation of electric charge. That is, any electric charge that you can observe in the universe comes actually as in discrete packets, with the packet being E in this case. Now, this is a second checkpoint that you can also try to answer.